All right, let's talk about motion in 2 dimensions then. A couple vocab terms you have to know is a projectile is an object shot through the air, so it could be a baseball, it could be a bullet, it could be anything. We're going to use that term quite a bit. Trajectory is its path through space. Let's take a look at that trajectory then. I've drawn some vector diagrams here, right here, to hopefully help make sense of. So here's some vectors to hopefully help you understand what's going on with the overall velocity of an object as it travels through 2-dimensional space, right here. So it rolls off this table, and right now on the table it has no vertical velocity whatsoever. At this point you can see now the vertical velocity vector starts to grow and get bigger through time, while the horizontal velocity vector stays the same. And so if you draw those vectors on the projectile itself, you can see how the overall velocity then is the the resultant of those two vectors as you add them, make a right triangle and add them, or make a parallelogram, either way. And you can see what happens to the overall velocity. The object starts, it changes and starts going more towards the ground, which explains the parabola that it flies through. All right, so here's another one then. This time instead of starting from the highest point, we start this off from some angle. Okay, so I've drawn the velocity vectors on there, and you can see what happens is this velocity vector is the only one that changes. The horizontal velocity stays the same if we ignore air resistance throughout the whole problem. So that length of that vector I tried to keep the same. But you can see the vertical velocity is decreasing at a constant rate. We know what that rate is. It's 9.8 meters per second squared. Until it gets to the top when there is no vertical velocity anymore. And then it keeps accelerating and it keeps losing velocity at that same rate, negative 9.8 meters per second squared. So that's an important spot right there. We're going to use the information we know about this to help solve a lot of problems in the future, because we know another piece of information here. We know that the vertical velocity at this point is 0. Let's say a ball is launched at 4.5 meters per second above horizontal. What's the maximum height and flight time of the ball? All right, so I wrote down all this information. So we have the velocity in the x direction. If you do the cosine, you'll get that. So I'll write that down. That would be cosine of 66 degrees equals adjacent, which is the initial velocity in the x, over hypotenuse, which is 4.5. So multiply both sides by 4.5. When you do 4.5 cosine of 66, you should get 1.83 meters per second. You do the same thing for the initial velocity in the y now. You would do, sine of 66 gives you opposite over hypotenuse. So if you multiply both sides by 4.5, that gives you 4.11 meters per second. Now we know the final velocity is going to be 0 because we talked about this thing stopping at its highest point. And once again, up here, we had mentioned at the highest point, that key spot right there, we know that the final velocity at that spot is 0. Okay? So we know the acceleration then is negative 9.8 meters per second squared. Initial distance starts off at 0. We're trying to find the maximum height. We're trying to find this right here. And we don't know the time either. So once again, we plug into the same equation we plugged into in the past, which is distance final equals initial distance plus initial velocity times time plus 1/2 average acceleration times time squared. So that's distance with average acceleration formula on your formula sheet. Plug into it, initial distance is 0. Plug it in, you should get this equation right here. Now this is a quadratic that opens down. This might look familiar to you guys that have studied quadratics. It looks like this if you graph it with your calculator. Now there's different ways to find the maximum height now, but this is an equation for distance in terms of time as a quadratic relationship. So we know it looks like this right here. And we need to find that maximum right there because that maximum point represents the time at which it reaches its maximum height. So if we find that by doing second calculate maximum on the calculator, you do second calculate maximum, scroll to the left of that point and hit enter, scroll to the right of that point and hit enter, and enter for the third time. That's probably the easiest way to get it, and you'll get time as 0.419 seconds. Doesn't take much time because this thing wasn't launched very fast, but it reaches maximum height in about half a second, 0.419. And we want to know that maximum height. Well, the maximum height is only 0.86 meters, so it doesn't even go a full meter in the air because it's not launched very fast. There are other ways to find this maximum height. One of the things that you could do is use what you guys know about the vertex of a parabola. The vertex of a parallel, the x-coordinate of the vertex is negative b over 2a, you learned from math class. So if you didn't have a calculator, you could just do this. Negative b would be positive 4.9 over 2 times a, which is 4.11. That would give you the time, which is 0.419. And you can plug that back into this equation to get the corresponding height, distance final, which is 0.86. So you don't need this calculator feature. If you don't have it, you can use what you learned about in math class. All right, so the last question then, it says a player kicks a football from ground level with an initial velocity of 27 meters per second, 30 degrees above horizontal. What's the ball's hang time? We'll also get the maximum height and the range. Okay, so I always write down the information again. We have x and y information. I'm going to draw a picture of this thing. 30 degrees above horizontal is the angle. And then 27 meters per second is the overall initial velocity. So I can then find the initial velocity in the x here and the initial velocity in the y here by using sine and cosine. So the cosine of 30 equals initial velocity in the x over 27, and the sine of 30 equals initial velocity in the y over 27. Multiply both sides of these equations by 27, and you'll find the initial velocity and the x and the y, which gives you 23.4 meters per second in the x direction. In the y direction, you get 13.5 meters per second. So I'm going to write that down here. Initial velocity in the x, which we can just call velocity in the x, because it's going to stay the same, is 23.4 meters per second. The distance in the x, I don't know. It's one of the problems I'm going to solve later. Time, I don't know. Initial velocity in the y is 13.5 meters per second. Final velocity in the y, I don't know. Acceleration, negative 9.8 meters per second squared. Initial height starts off from 0, from the ground, and reaches some maximum height, which I'm going to find hopefully here. And the time is, I don't know. Okay, so I'm going to look for an equation that relates distance, acceleration, and initial velocity, because that will help me find my final velocity. And then from there, I'm going to try to find my time as well. So that equation on your formula sheet is final velocity squared equals initial velocity squared plus 2 average acceleration times change in distance. Final velocity is what I'm looking for. Initial velocity is 13.5 plus, this would be 2 times the average acceleration, which would be 2 times negative 9.8 times the change in distance, which I'm sorry, I don't have the change in distance, so this formula is going to give us an equation with 2 variables. That doesn't help. Let me try this again. All right, actually I can use this, but what I'm going to do is I'm going to stop the problem at when it reaches its maximum height. So my final velocity would then be 0 meters per second. So I'll plug in 0 right there, because if like we talked about before, when the ball reaches its maximum height, it doesn't have any vertical velocity for a second there. So let's stop the problem there, and let's just keep in mind that time that we get is at that point. So this would be, I'm going to solve this for the change in distance. Move this over to the other side, divide by 2 times 9.8, and you get a change in distance, in this case, is about 9.3 meters. So distance final would be about 9.3 meters. That's going to be the maximum height then, because that's the distance final that we're looking for. So that would answer question B here, 9.3 meters. We still need to find the hang time though, so that's the height, the time. So to do that, let's use, there's different ways we can do it, but let's use distance final now equals distance initial plus initial velocity times time plus, we can actually use this. Acceleration equals change in velocity over change in time would be easier, because we know the acceleration is negative 9.8. We know the change in velocity is 0 minus 13.5, so we can solve for the change in time. Multiply both sides by t, divide by negative 9.8, and you get the time, or the change in time, is about 1.38 seconds. So about 1.38 seconds goes by, and that would be the hang time. And so we would enter that in for part A. And then for part, the last part says the ball's range, so that's how far it goes. Okay. To find how far it goes, what we can do is take this time then in the x direction and use our equation of velocity equals distance over time. So we're going to multiply the 23.4 by the 1.38, and that gives us about 32.2 meters for the range. That's how far it goes total. Okay, hopefully this helps a little bit. We'll do some homework problems as well.